Hello everybody and welcome. This is Areas Under a Curve. Let's continue doing our amazing exploration of integrals. And remember the last videos we left off, we defined areas under a curve as an integral. We're no longer taking the summation of infinitely many rectangles, but rather we are rewriting it as an integral and they represent the same thing. So what do we mean by that? If we have a function f of x, we go from a to b. Instead of doing infinitely many rectangles, we say that this area is a number and the area is equal to the integral from a to b of whatever function with respect to x. That's the summary of the previous ones. So let's actually learn some properties of this definite integral. Remember, definite versus indefinite integral. Properties of definite integrals. Well, one, if f is defined at x equals a, then the integral from a to a under the function, of f of x, d of x, is equal to 0. Why is that? Because remember, this is saying this is the area from a point A to a point A. This is the area under a curve from 1 to 1, under a curve from 3 to 3. So if I were to draw that, how would that look like? I'm going from A all the way to, to A again. So how much area have I accumulated? That was going to become a keyword as we move on. How much area have I accumulated under the curve? Well, from point A to point A, I have accumulated 0 area. So the answer is 0. The next one is if f is integrable on a closed interval from a to b, then the integral from b to a is equal to f of x dx. No, wait. If the integral from b to a of f of x dx is equal to negative the integral of a to b of f of x dx, what is this really saying? It's saying, well, we've explored when all the a's have been less than b's. Now we explore the fact when the a was equal to b, right? Under a curve from an a to a b. We explore when it's from a to a. Now this one is saying, well, what happens when a is greater than b? All right, pretty much it's kind of like in the negative direction. Well, this one is really simple. We have this property, well, it is the inverse of that. So, example, the integral from 5 to 2 of f of x dx will be equal to, well, you put a negative in front of it to show that it's the inverse direction. The integral from, now you flip your limits of integration from 2 to 5 of f of x dx. So you're coming in this type of scenarios when you see a geometric figure mostly and you have area under a curve. All right. And they're like, oh no, or something like that. Here's another example. What is the area under the curve of the graph of sine of x? Remember how do we graph sine? Well, this will be cosine because it's like a little s. Well, I'm not interested in cosine. I'm interested in sine. So it's a little s then. There you go. That's my little trick. So what is from pi to pi? Well, what is the, and it will continue. What is the area under the curve from pi to pi? Well, it is 0. There is no area and there's no number to be covered from a lower bound to an upper bound of integration. And now this one is what I was referring. So on this one, what is the integral from 3 to 0 of x plus 2 dx? And this one is saying what is the area under the curve from x equals 3 backwards all the way to 0 under the same function. The function has not changed. Well, this one, remember, this is the property from the top that we can just rewrite it as the integral from 0 to 3 of x plus 2 dx, but we have to write a negative in front of it. So, and remember, what is this? What is the integral from 0 to 3 of x plus 2? Well, we have it. We did it on the previous video, and the interval, the value for that, I believe, was equal to 21 over 2. But since we have this negative in front of it, it's like equal to negative 1 times 21 over 2, which is equal to negative 21 over 2. Check the previous video if you need a refresher on this one, okay? So let's move on to more properties of integrals. So that will be the next video.